All right. In this video, we will be going over section 2.3. This section is about rules for calculating basic derivatives. Okay. All right. I want to start with this theorem, theorem 2.8, derivatives of constant, identity, and linear functions. Okay. So here is what the theorem says. For any real numbers k, m, and b, we have d over dx k is equal to 0. In other words, the derivative of k with respect to x is equal to 0. And then the derivative of the function, identity function, x is equal to 1. Okay? This is the function. This is where you put your function that you are taking the derivative for. Okay? So you are taking the derivative of this function x, the derivative of this identity function is 1. Okay? And here you have a linear function, mx plus b. The derivative of this linear function is denoted by d over dx mx plus b. The derivative of that function would be equal to m. Okay? So I'm not going to prove all of this, but let's quickly prove this one. Let's prove that the derivative of this linear function mx plus b is nothing but the m. M is the coefficient of x. Okay, in this linear function, the coefficient of x is m. That is going to be the derivative of this whole function that you have here. Okay, again, this notation is for the derivative. Okay, you write d over dx, and then within parentheses you write your function. That means the derivative of that function. Okay, d over dx mx plus b means the derivative of the function mx plus b. All right, let's quickly prove the part C, and I will leave the other parts as an exercise. That's going to be very straightforward. Okay, C. Let's prove this one. Well, to prove that, I'm going to take this function to be f of x. Okay, I'll take this to be f of x. I want to find the derivative of f of x. That means f prime of x, right? So we have df over dx. By definition, we have limit as h approaches to 0, f of x plus h minus f of x divided by h. Okay. Again, this is nothing but f prime of x. Okay, the derivative of the function f. Okay, let's try to see whether this derivative is equal to m. Let's calculate this limit. To calculate that limit, I will simplify my numerator. Limit as h approaches to 0, f of x plus h. To find f of x plus h, I'm going to have to plug in x plus h in my function f. This is my function f of x. Okay. Then you get m times x plus h plus b. Plus b. That's what you get if you plug in x plus h in this function. You replace this x by x plus h. Then you get m times x plus h plus b. And then don't forget you have minus f of x in the top. Minus f of x. My f of x is m times x plus b. Everything divided by h. Now it's all about cleaning up the top. Notice that when you clean up the top, if you distribute this negative sign, you have minus mx minus b. You have a plus mx here. That plus mx will be cancelled with this minus mx. And here you have a plus b, and that will be cancelled with this minus b. Okay. What you have in the top would be limit as h approaches to 0. You will have m times h. That's all remaining in the top divided by h. Okay. I just did the cancellations. If you remove the parentheses here and remove the parentheses here, you will see the cancellation. The only remaining term is m times h. That is this term, m times h. That's the only remaining term. Other terms will be cancelled. Now, as you can see by cancellation law, I can cancel this h and this h. Okay, so I get limit as h approaches to 0, m. Notice that m is a constant. So the limit is m itself. That's what we wanted to prove. Okay, so the derivative of a linear function of this form is equal to m. That is nothing but the coefficient of x. And it makes sense because we know that if we have a straight line of this form, y is equal to mx plus b, the slope is m, right? Slope is nothing but the derivative. Derivative and slope, they are synonyms, as we discussed in section 1.2.1. All right, let's move on. Now let's try to apply this this theorem to some of the examples. Okay, here again, let's recall the theorem. If you have a constant, the derivative of a constant is equal to 0. If you have the identity function, the derivative of the identity function d over dx, x is equal to 1. Or in other words, the derivative of the identity function is equal to 1. And the derivative of a linear function is given by just m. You take the coefficient of m. Okay, so let's work on these two examples real quick. What is f prime of x using the previous theorem? It's clearly 0, right? Because you have a constant here. F of x is a constant. The derivative of a constant is 0 by previous theorem. And then here again, the answer is immediate. G prime of x is equal to minus 5. That is the value of m. Your value of m in this case is minus 5. Okay, all right, let's move on. Next, we have this very powerful rule called the power rule. Okay, this is an extremely important differentiation formula in this chapter. Okay, what this rule tells you is that for any, this is of course the theorem 2.9. Okay, for any non-zero rational number k, this k can be any non-zero rational number. Notice that a rational number is a number of the form p over q, where p and q are integers, but q is not equal to 0. You know why q is not equal to 0, right? You cannot have 0 denominator. Okay, so any number of this form is called a rational number with p and q being integers, with q is not equal to 0. Okay, so if k is any rational number, then d over dx, x to the power k. What does that mean? The derivative of x to the power k. Okay, here is the notation for that. D over dx, x to the power k. That means the derivative of the function x to the power k. Okay, I'll take this function to be f of x. Okay, for further calculation. Okay, now what this tells you is that the derivative of the function x to the power k is equal to k times x to the power k minus 1. Very simple rule. Okay, but very useful. What you do is you pull this k to take the derivative of this function, you pull this k to the front. That's how you get this k in the front. And then you reduce the power by 1. Earlier you had power k, now you have power k minus 1. Such a simple rule. You pull this power to the front and then reduce the power by 1. That's when you get this. Okay, so the derivative of x to the power k is k times x to the power k minus 1. All right. Next, I'm going to prove this rule for the case when k is a positive integer. Okay, the proof of this theorem for the case when k is a general rational number can be done using implicit differentiation. We will discuss that in the implicit differentiation section, but we will not be going over the proof, but I'll be giving some hints. Okay, but here we will prove this theorem for the case when k is a positive integer. Okay, assume that k is a positive integer. Proof. Assume that k is a positive integer. Okay, then I'm going to use the derivative definition of the derivative to find the derivative. Okay, so I take my function to be f of x. Remember, so by definition, my f prime of x is going to be limit as h approaches to 0. Actually, I'm going to use the c definition here. Okay, as z approaches to x, f of z minus f of x divided by z minus x. That's the second definition of the derivative. Okay, I'm using that definition. Even if you use the other definition, you can still get the answer. Okay, no problem. But this definition would be easier in terms of notations. All right, what is this? Limit as z approaches to k, z to the power k minus x to the power k. Because your f of c is z to the power k, because my function f of x is nothing but x to the power k. So f of z should be z to the power k. F of x is, of course, x to the power k. Don't forget z minus x in the bottom. Okay. Now what I'm going to do is I'm going to use some product formula, okay, that can be verified easily. So this is equal to, this whole thing is equal to, I'll put the equal sign here if you don't mind, limit as z approaches to x, the z to the power k minus x to the power k is equal to this product, z minus k times c to the power k minus 1 plus c to the power k minus 2, pardon me, here z to the, c minus x, okay, c minus x times x to the power 1 plus z to the power k minus 3 times x to the power 2 plus blah, blah, blah. Finally, you get z to the power 2, z to the power 1, x to the power k minus 2 plus x to the power k minus 1. Okay, so that's what you get. This is k minus 1, by the way, right? A little bit smaller. Okay, that's what you get. In the bottom, don't forget you have z minus x. Actually, this is equal to this product. This can be easily verified. How would you verify this? How do you verify that these two things are equal? Well, all what you do is you distribute this. You multiply this by this, this by this, this by this, this by this, this by this. And then you multiply this by this, this by this, pardon me, this by this, this by this, this by this, this by this, this by this. And then you will see that you have a bunch of cancellations. Only thing remaining is this difference, z to the power k minus x to the power k. Okay, the proof is so straightforward. So I'm not going to show the proof. This is the same thing as c to the power k minus x to the power k. Now something very interesting happening. By the cancellation law, I can get rid of this c minus x and z minus x in the bottom. Okay. Now I can take the limit. If I take the limit now, as z approaches to x, to find the limit as z approaches to x, you have to replace your z by x, right? Because as z approaches to x, this becomes x, this becomes x, this becomes x. Okay, so if I replace z by x, you get x to the power k minus 1 plus, notice that if you plug in x here, you have x to the power k minus 2 times x. That is x to the power k minus 1. Again, that is x to the power k minus 1. Likewise, you can see that whenever you plug in c is equal to x, you get x to the power k minus 1. Because here, if you plug in x, you have x to the power k minus 3 times x to the power 2, which is x to the power k minus 1. Everywhere you get is copies of x to the power k minus 1. At the end also, you have x to the power k minus 1. Okay. Now, notice that these are like terms, x to the power k minus 1 everywhere. So how many of do you have here? There are k of them, because see, there are k terms here. If you count these terms, you have k terms here. So the answer should be k times x to the power k minus 1, because you have k copies of x to the power k minus 1. Okay, that will be k times x to the power k minus 1. So that completes the proof. As you can see, the derivative f prime of x is equal to k times x to the power k minus 1. Okay, that is the proof for the case when k is a positive integer. When k is a general rational number, when k is of the form p over q, we can prove it using implicit differentiation I will discuss a little bit about implicit differentiation, how to prove this using implicit differentiation when we come to that section. Okay. All right. Okay, now let's work on some examples to understand this power rule. Okay, so these are the examples that I want to go over. What about the first one? What is f prime of x? We are asked to find the derivative of each of the following function. Okay, what is the first derivative of the first function? Someone might think this as the power, so it should be like 3 times 5 to the power 2, right? Because your power comes to the front, and then this is reduced by 1, so it becomes 2. But no, that's wrong. Okay, notice that at the end of the day, this is a constant. 5 to the power 3 is 125. That is a constant. The derivative of a constant is 0. We already realized that in the theorem 2.8, the derivative of a constant is 0. Okay, don't get distracted if you see something like this. Okay, if it is a constant, derivative is 0. Okay, next one, g prime of x. The derivative of the function g is equal to, so straightforward, you pull the power to the front, x 3 times x to the power, and then you reduce this power by 1. Then you get 2. That is the derivative. Okay, it's so straightforward and it is so powerful. Okay, so you can easily find the derivative of a power function using that rule. What about the next one? What is h prime of x? That is, again, I am pulling my power to the front to the power x to the power times x to the power, and then I have to reduce this power by 1. Okay, so you get minus 3 minus 1. I'm reducing the power by 1. Remember, it should be k times x to the power, k times x to the power, k minus 1. So I have, this is your k, you pull the k to the front, k times x to the power, k minus 1. What would that give you? That is equal to minus 3 times x to the power minus 4. If you don't like to keep the negative exponents, you may write this as 3 over x to the power 4. Either way is fine. This answer is also acceptable. Okay. All right. Finally, the last one. What is this one? Maybe I'll put a line in between. What is k prime of x? Again, the same rule. I pull my power to the front, x to the power 8 over 7 minus 1. Okay, the power should be k minus 1. That's why I have 8 over 7 minus 1. Okay, so what would you get if you simplify this? 8 over 7 times x to the power 1 over 7. That's the answer. Okay. It's a so straightforward applications of the power rule. Okay. All right. The next thing I want to talk about is this particular theorem, Theorem 2.10, derivatives of constant multiples and sum of functions. Okay. Here is the constant multiple rule. If you have a product of a constant and a function, k times f of x, the derivative of that would be k comes out and then times the derivative of f prime of x. Okay, or simply what it tells you is that if you have a constant times a function, to take the derivative of that whole thing, what you do is you pull this constant out and take the derivative of the function. So that's why you have this k in front. Okay, k stays as it is in the front and you take the derivative of the function. And the next rule is the sum rule. If we have sum of two functions, the derivative of the sum of two functions is equal to the sum of the derivatives. Or in other words, if you have a sum and if you want to take the derivative of that sum, you take the derivative of each individual function and add them together. That's what we do. We have a similar rule for difference. Okay, this is the difference rule. If you have a difference of two functions and if you want to take the derivative of that difference, you take the difference of the derivatives. Or in other words, you take the derivative of each individual term by maintaining this negative sign in the middle. Okay, all right. Again, here, I'm not going to prove all of these rules, but I will prove the sum rule, and rest of the things are very similar. I will leave that as an exercise for you. Okay. All right, let's try to prove the first one. Okay, by definition, proof. By definition, f plus g prime of x is equal to limit as h goes to 0, f plus g of x plus h minus f plus g of x divided by h, right? That's the definition. This is the definition of the derivative of f plus g. F plus g prime of x is f plus limit as h goes to 0, f plus g of x plus h minus f plus g of x divided by h. Now I'm going to do some arrangements here. I'll put my equal sign to the left here. Then I have limit as h goes to 0. I'm going to make some simplifications here. So by definition, this can be written as okay, by definition, I can rewrite this as f of x plus h plus g of x plus h. Okay, that's by definition that you learn. Definition of a function, sum of functions that you learn in your pre-calculus class. Okay, f plus g of x plus h is same as f of x plus h plus g of x plus h. Here also similarly, f plus g of x is same as f of x plus g of x. Okay, don't forget this minus sign in the middle. Now I'm going to rearrange terms here. Here you have f of x plus h. Here you have a minus f of x. I'm going to write those two terms together. Okay, I'm going to rearrange my top. Limit as h approaches to 0, f of x plus h minus f of x, and then I'm going to write these two terms together again. Here you have minus g of x because you have minus sign here. You have minus g of x, and here you have g of x plus h. So I'm going to write those two terms together. G of x plus h minus g of x. Now notice that I have h in the bottom. So I'm going to put that h underneath of this expression and underneath of this expression. That's the same thing. Because I splitted these two, I paired these two terms and I paired these two terms. Then this is the first expression. I put my h underneath of that expression plus, and then I put my h underneath of this paired expression. That is g of x plus h minus g of x. Okay. All right. Now what I'm going to do is I'm going to take the limit. Okay. I'm going to take, this is a summation of two functions. This is a function. This is a function. So I can send this limit inside, distribute this limit using the limit rules that we discussed in chapter 1. Okay. So if I take the limit of these two, you get limit as h approaches to 0, f of x plus h minus f of x divided by h plus limit as h approaches to 0, g of x plus h minus g of x divided by h. This is equal to, what is this? Is this something familiar to you? This is the derivative of f, right? By definition. By definition of the derivative, this is the derivative of f. That is f prime of x. By definition, this part is the derivative of g of x. So this should be g prime of x. Sorry, I have a small little room here. So that would be equal to f prime of x plus g prime of x. That's what you wanted to prove. Okay. The derivative of the summation of f plus g is same as sum of the derivatives. That's what we have established here. All right, let's move on. As I said, I'll be leaving these two as an exercise for you. Okay, make sure that you work on them. Okay, let's do some examples to understand what's going on here. Let's work on the first example. This example, find the derivatives of each of the following function. Okay, let's find the derivative of this function first. Part A, f prime of x. How do you find the derivative? First of all, notice that using the sum rule, you can take the derivatives of each individual function. By the way, this sum rule tells you that how to differentiate when you have sum of two functions. Even if you have sum of more than two functions, you can have a similar argument. For example, if you have f plus g plus k prime of x, that is equal to f prime of x plus g prime of x plus k prime of x. Okay, think of this as summation of three functions. This is the first function, this is the second function, this is the third function. Then to take the derivative, you take the derivative of the first function plus the derivative of the second function plus the derivative of the third function. Okay, let's do that. How do you take the derivative of the first function? Notice that it looks like a constant times another function. In that case, we have constant multiple rule right here. If you have a constant, you can pull that constant out and you can just deal with the derivative of the function. Okay, that's what I'm going to do here to differentiate this one. This is a constant. I'm going to pull that constant out. 2 will stay out. 2 will stay there as it is. And I'm going to take the derivative of this function. The derivative of this function, we know by power rule, that will be 5 times x to the power 4. I pull this power to the front, that's when I get 5 here, and I have to reduce the power by 1. 5 minus 1, which is 4. And then I'm going to deal with the second function. This is the second piece of function. Again, I'm going to leave that constant out as it is, 5, times I'm going to take the derivative of x to the power 3. That is 3 times x to the power 2. And then plus, finally, I have this particular function, which is a constant function. What is the derivative of a constant function? 0. This is the answer. If you want, you can simplify this a little bit. 2 times 5, 10 times x to the power 4 plus 5 times 3, 15 times x to the power 2. Okay, so that's the derivative. What about the second one? Part B. G prime of x. There we can apply the difference formula, right? You have a function minus another function. Then all what you do is to take the derivative of g of x, take the derivative of the first function minus take the derivative of the second function. Let's do it. The derivative of the first function is minus 3 over 2 times x to the power minus 3 over 2 minus 1. Remember the power rule? The derivative of x to the power k is k times x to the power k minus 1. Okay, that's what I'm applying here. I have k times, this should work to the front, k times x to the power k minus 1. And then minus here, see, 3 times x to the power 3. So 3 is a constant. I'm not going to mess with that constant. I'm going to leave that constant as it is. Minus 3 times. 3 times x squared. You take the derivative of x to the power 3. It becomes 3 times x to the power 3 minus 1. 3 minus 1 is 2. Now I can simplify this further. This is x to minus 3 over 2 times x to the power minus 5 over 2. Okay, if you simplify this, you get minus 5 over 2. Minus 9 times x squared. That is the derivative. Done. Okay. All right, let's move on. That's an application of these 3 rules: constant multiple rule, sum rule, and the difference rule. Okay. Okay, next we have a few more rules. Theorem 2.11, derivatives of products and quotients of functions. Okay, so basically here we are going to discuss the product formula and the quotient, product rule and the quotient rule. If f and g are functions, then for all x such that both f and g are differentiable, we have the following differentiation formulas. Okay, so here are the formulas. Here is the product rule. If you have the product of 2 functions and if you want to take the derivative of that product, that is equal to f prime of x g of x plus f of x g prime of x. Okay, it is very easy to remember this formula. What you do is you differentiate a one function. There are 2 functions associated here, right? you have f and g, you differentiate one function and leave the other one fixed. And then you put a plus sign, and then you leave the first one, the one you differentiated in the previous step fixed, and you differentiate the other function, which was fixed earlier. Okay, so that you can use that idea to remember this. Okay, you always leave one function alone, one function fixed. Okay, all right, that's the sum rule. And then quotient rule, f over g prime. Okay, so this is how you take the derivative of a quotient. You have a quotient f of x over g of x. Then how do you take the derivative of that quotient? Here is the quotient formula. Okay, f prime of x times g of x minus. Remember this minus sign. Okay, don't get confused with this rule. Here you have a plus sign in the product rule. Here in the quotient rule you have a minus sign. F of x minus g of x. If you notice, these two, this one and this top, look exactly the same except for this minus sign. Okay, this sign is switched here. Divided by g of x squared. This is what we call the quotient rule. Okay. Again, I'm not going to prove both of these formulas, but I will prove one of them. Okay, let's prove the product rule real quick. So by definition, f times g prime of x is equal to limit as h goes to 0, f times g of x plus h minus f times g of x divided by h. This is the derivative of the product f and g by definition. Okay. Now by definition of product of two functions f and g, f times g of x plus h is the same as f of x plus h times g of x plus h. Again, this is something that you learned from your pre-calculus class. This is basically how you multiply, how you define the product of two functions f and g. Okay, this f times g of x plus h is same as f of x plus h times g of x plus h. Similarly, here f times g of x is same as f of x times g of x. Now let's do some constructions here. Limit as h goes to 0, f of x plus h times g of x plus h. Here is the construction I'm going to do. I'm going to subtract f of x times g of x plus h. I'm going to add that term. Then they will be cancelled, right? F of x times g of x plus h. Finally, I have minus f of x, g of x divided by h. All I did was I subtracted f of x, g of x plus h, and I added f of x times g of x plus h. As you can see, these two will be cancelled, right? You get this back. We have done nothing wrong to this expression. This expression is same as this expression. Okay, because these two will be cancelled and you get back your top. Okay, so now what I'm going to do is I'm going to pair terms. I'm going to look at these two things and I'm going to pull out the g of x plus h. As you can see, g of x plus h is common for those two terms. Then you get limit as h goes to 0, g of x plus h times f of x plus h minus f of x. And then from the remaining two terms, from these two terms, I'm going to pull out the f of x. Then you get f of x times g of x plus h minus g of x, everything divided by h. Now, think of this as your first expression plus this is the second expression. You have a common denominator, so I can put that denominator underneath of this expression and underneath of this expression individually. Okay, so this is equal to limit as h approaches to 0, g of x plus h times f of x plus h minus f of x divided by h plus f of x times g of x plus h minus g of x divided by h. All I did was I put this h underneath of this expression and I put the same h underneath of this expression because this is a summation, this plus this. Okay. Now I can take the limit. Okay. I can distribute this limit. Of course, I should have big parentheses around. I can distribute this limit to the first expression and to the second expression by the limit rule that we discussed in chapter 1. If you take the limit of the first expression, notice that I'm going to take the limit straight away, okay? Maybe I'll write one step, limit h goes to 0, g of x plus h times f of x plus h minus f of x divided by h plus limit as h goes to 0, f of x times g of x plus h minus g of x divided by h. Okay. Now, as you can see, this is a product, this times this. You can take the limits of the product. Okay. Limit of this product. So you take the limit of the first expression and the limit of the second expression. As you can see, as h approaches to 0, the limit of the first expression is g of x because this h goes to 0. Okay, as h approaches to 0, this will be going to 0. So that means this becomes g of x. This is equal to g of x times what is the limit of this expression as h approaches to 0. That is, by definition, f prime of x. Plus similarly here, you have f of x. The limit of this as h approaches to 0 is fx itself because there is no h involvement here. So that is f of x itself. The limit of this expression, pardon me, limit of this expression as h approaches to 0 will be g prime of x by definition. Okay, that is what we wanted. F prime of g of x plus f of x times g prime of x. F prime of x times g of x plus f of x times g prime of x. That's what exactly we have here. Of course, you have to switch these two terms. Since it is a product, the answer is the same. Okay. Maybe let me quickly write that by switching terms. F prime of x, g of x plus f of x, g prime of x. All right, that completes the proof, and I will leave the second part as an exercise. Okay. Okay, next let's look at some applications. Here is the example that I want to go over. Find the derivatives of each of the following function. Here is the first function given to us. K of x is equal to this function times the second function. How do you find the derivative of this one? Well, we can easily apply the product rule, right? If you have a product of functions, f times g, the derivative of that would be f prime of x g of x plus f of x g prime of x. Okay, all what you need to do is you need to identify this as a product of two functions. For that, I'm going to identify this first piece as my f of x, the second piece as my g of x. Then the derivative of this product, or in other words, k prime of x. K prime of x is the derivative of this product. Okay, so will be, you can straight away use this formula. According to this formula, it is equal to f prime of x g of x plus f of x g prime of x. Let's find f prime of x. Okay, first let me write the formula actually. F prime of x g of x plus f of x times g prime of x. That's what the formula tells you. Okay, let's fill in the gaps. What is f prime of x? How do you find f prime of x? Here is your f of x. You take the derivative of this function. This is a sum of two functions, the derivative of this one plus the derivative of this one. Okay, so the derivative of the first function will be, maybe I will show you the work here since this is the first couple of examples. Your f of x is equal to x squared plus 1. So f prime of x is equal to the derivative of this one plus the derivative of this second function. The derivative of the first one is 2 times x to the power 1. I don't really have to put a 1 here. I can just write x. And the derivative of the second function is 0. This plus 0, of course, that is 2x. Similarly, you can find your g of x is given to be x to the power 1/3 plus 5. So g prime of x would be, you take the derivative of this one plus the derivative of this one. This is 1/3 times x to the power minus 1/3 minus 1 plus 0. The derivative of 5 is 0. Okay, if you simplify this, you get 1/3 times x to the power minus 2 over 3. That is the derivative of g, or g prime of x. Okay, now we have everything in our hand. Let's go with this formula now. F prime of x, that is this one. 2x, g of x times g of x. My g of x is x to the power 1/3 plus 5 plus f of x. F of x, my f of x is this one, x squared plus 1 times g prime of x. G prime of x, I just found it, is 1/3 times x to the power minus 2/3. That's it. That is the answer. Okay. All right. Let's work on the second example now, second part now. We need to find the derivative of this one. Here clearly we are going to use the quotient rule. Okay. Here is the quotient rule. Here is how you differentiate a quotient, f of x divided by g of x. You have a quotient here, of course. This is your f of x. This is your g of x. So let me take this as your f of x, the top function. The bottom function is g of x. Okay. Then to go with this formula, I need f prime of x and g prime of x, right? So let's find them here. My f prime of x would be clearly 3x squared minus 1. Would you agree with me? The derivative of the top function, derivative of f of x is the derivative of this function minus the derivative of this function. The derivative of this function is 3 times x squared using the power rule. Remember, recall that the power rule is, if we have x to the power k, the derivative of this one is k times x to the power k minus 1. I just applied this rule here to get the 3x squared. And then what is the derivative of x? Well, x means x to the power 1, right? So the derivative of that would be 1 times x to the power 1 minus 1, which is 1 times x to the power 0, which is 1. Okay, that's how I get minus 1 here. Of course, we have a minus sign here. So that minus sign comes here, and the derivative of x is just 1. Okay, now I need the derivative of h. Derivative of g. G prime of x is just 2x, because the derivative of this function is derivative of the first piece plus the derivative of the second piece. The derivative of the first piece is 2x. The derivative of the second piece, which is a constant, so it's 0. 2x plus 0, which is 2x. Now I'm ready to go with this formula. I have all the ingredients that I want to go with this formula. So h part b, okay? H prime of x is equal to f prime of x, that is 3x squared minus 1 times g of x. Your g of x is x squared plus 1 minus, in the middle you have a minus sign, okay? If you look at this formula, you have a minus sign. and then f of x times g prime of x. F of x cubed minus x times g prime of x. G prime of x is 2x. Everything divided by gx squared, where gx is x squared plus 1. You need to have the square. Notice that you have g of x squared in the bottom, so it should be g of x squared. This is the answer. This is your answer. Okay, you can leave the answer as it is. If you want, if you are asked to simplify, you need to simplify this top. Okay, I'm not going to simplify that because it's too straightforward. But if you're asked to simplify it, you need to leave the simplified answer. Okay, let's move on. Let's work on some more examples. Here is the example. This is a kind of a little bit different type of an example. Let's go through this example. Given that f, g, and h are functions with values, f of 2 is equal to 2, g of 2 is equal to minus 1, h of 2 is equal to 1, and point derivatives, f prime of 2 is equal to 4. F prime of 2 means the derivative of f at x is equal to 2 is equal to 4. Here, g prime of 2 is equal to minus 2, h prime of 2 is equal to minus 5, and we are asked to calculate this. First one and the second part. Let's look at this one. How would you calculate this quantity? Well, let's apply the definition of the theorem that we learned about the sum of two, derivative of sum of two functions, or the sum rule. Here you have summation of two functions, right? And you have to take the derivative of that summation. So you can take the derivative of the first function plus the derivative of the second function. I'm going to apply that rule. Then you get 3f plus 4h prime of 2 is same as 3 times f prime of 2 plus 4 times h prime of 2. That's what you get. You take the derivative of this function and then plus the derivative of this function. What is the derivative of this function? Notice that this is a constant multiple of f of x, right? So this constant stays as it is. And you take the derivative of this function piece, that is f prime of 2, because you have 2 here. Okay, so that is 3 times f prime of 2 plus 4 times, this is again a constant, you just take the derivative of this function h, that is the constant multiple rule, right? If you have multiplication of a constant and a function, you leave the constant as it is, take the derivative of this function, h prime, which is at 2. So you have h prime of 2. Now your life is simple. 3 times, all these things are given. F prime of 2 is given. Your f prime of 2 is 4. 4, 3 times 4 plus 4 times h prime of 2. Your h prime of 2 is also given, which is minus 5. All you need to do is to simplify this. This is 12 minus 20, which is minus 8. Okay. Similarly, we can calculate the other expression, f over g prime of 2. Okay, this is the quotient rule, but we know the formula for quotient rule. Okay, all what you need to do is to get this one, you need to plug in x is equal to 2, right? Because you have x is equal to 2 here. You replace your x by 2. Then you get this is equal to f prime of 2 g of 2 minus f of 2 g prime of 2 divided by g of 2 whole thing squared. This is equal to, all these quantities are given. F prime of 2, g of 2, f of 2, f g prime of 2, all are given. So let's go ahead and plug them in. F prime of 2 is 4 times g of 2 is 2 minus f of 2. F of 2 is 2. Pardon me, g of 2 is not 2. Let's do it again. f prime of 2, which is 4 clearly, times g of 2. G of 2 is minus 1 minus f of 2. F of 2 is 2 times g prime of 2. G prime of 2 is minus 2 divided by g of 2 squared. G of 2 is minus 1 squared. Okay, it's all about simplifying this expression. This is minus 4 plus 4 divided by minus 1 squared, which is 0. Okay, so the answer is 0. All right, that's a different type of an example. Let's move on. This is the last example that I want to discuss. This is also a very important type of problem, very interesting example. If possible, find constants a and b so that the function f that follows is continuous and differentiable everywhere. If it is not possible, explain why not. Okay, let's work on this one. What do you want here? We want this function to be continuous and differentiable everywhere. But when x is less than 1, you have a nice continuous and differentiable function because we are given that a and b are some constant. Okay, then this is a nice, smooth, continuous function, continuous and differentiable function when x is less than 1, and also when x is strictly greater than 1. Here you have greater than or equal sign, but think about when x is strictly greater than 1, this is the function. This is again a differentiable function when x is strictly greater than 1. Okay, because it's clear, because this is a power function, this is a constant function. Okay, combination of power function and constant function, they are again differentiable. We know that means we know that this function is differentiable when x is strictly less than 1. This is differentiable when x is strictly greater than 1. Okay. Remember, we want this function to be continuous as well everywhere. Okay. That means the question is that whether this function is continuous and differentiable at this breaking point. If we can make sure that at this breaking point, that means at x is equal to 1, this function is continuous and differentiable, then we are good. We can find those a and b. Okay, so let's try to make sure that this function is continuous at x is equal to 1 and also differentiable at x is equal to 1. So what do you want to make sure if you want to make sure that your function is continuous at x is equal to 1? That means your function value should be the limit value, right? Your left limit and the right limit should be equal to the function value. First of all, I'll write for continuity. Let's argue the continuity first. For continuity, we need f of 1 is equal to the left limit as x approaches to 1 from the left-hand side. F of x is equal to limit, the right limit, as x approaches to 1 from the right-hand side, f of x. Okay, that's what we need for the continuity. For the continuity, we want the left limit and the right limit, they should be equal. That means the two-sided limit exists. Okay, if your left limit and the right limit are, they exist and they equal, what that means is that the two-sided limit exists. Limit as x approaches to 1, f of x exists. And that should be equal to the function value at x is equal to 1. Okay, let's find them. The function value at x is equal to 1 is clearly f of 1. You plug in x is equal to 1 in this function, right? Because you have x is greater than or equal to 1 here. So f of 1 is b minus 1. Okay, and then how do you find the left limit? Okay, to find the left limit as x approaches 1 from the left-hand side, f of x, you plug in x is equal to 1 in this phase. This is the function when x is less than 1. Okay, that means to the left of 1. So you plug in 1 in this function. That is going to be a plus b. What is the right limit? Limit as x approaches to 1 from the right-hand side, f of x is equal to find the right limit, you plug in x is equal to 1 in this function. Because this function is valid when x is bigger than or equal to 1, that means to the right of 1. So this is the valid function. You plug in 1 here, you get b minus 1. As you can see, your right limit is same as the function value. What do you want at the end of the day? End of the day, you want f of 1 should be equal to the left limit, that should be equal to the right limit. That means these two should be equal, right? Because this is already equal. This is equal to this one. So all what you need is these two should be equal. Your left limit and the right limit should be equal. That means you want a plus b equal b minus 1. Okay. Now, of course, if you move your b to the left-hand side, you get a is equal to minus 1. You have the value of a. Now, how do you find the value of b? To find the value of b, I use the I want to use the fact that I want my function to be differentiable at x is equal to 1. Okay, to make sure that, what I do is I take the derivative function f prime of x to the left of 1 and to the right of 1. When x is less than 1, my derivative. What is my derivative when x is less than 1? All what you do is you take the derivative of this function. This looks like mx plus b. So the derivative of this piece is just a. And then when x is greater than 1, I find the derivative of this function, which is 2bx. The derivative of this piece is 0, right? It is 2bx. Write it again, 2bx. Okay. All right. Now, what do I want? I want my derivative also to be equal. The left derivative and the right derivative should be equal at x is equal to 1 if I want my derivative to exist. Okay. So, to find the left derivative, I plug in x is equal to 1 in this function, because this is the derivative when x is less than 1, and this is the derivative when x is greater than 1. So, to find the left derivative, f prime of minus 1, I plug in x is equal to 1 in this function, which is a. To find the right derivative, I plug in x is equal to 1 in this function, which is 2b. 2b times 1, which is 2b. Now I want my left and right derivatives to be equal, because I want my function to be differentiable at x is equal to 1. So that means I want a is equal to 2b. This will give you, because we already know that a is equal to minus 1, I can find my b. b is equal to a divided by 2, which is minus 1/2. So we found the values of a and b so that my function is differentiable at x is equal to 1 and continuous at x is equal to 1. All right, that's the last example that I wanted to talk about. I'll stop there. I'll see you next time.